Yeah, so this is an action that you're doing on the set. And it takes A1 to A3. It takes A3 to A6. And it takes element A6 to A1. So if you rewrote this ordered set, it would be no longer A1 is the first element, right? The new first element is A6. A2 is the same. The element in place of A3 is now not A3, it's A1, or A1, up to, and then A6 becomes A1, and then the rest stay the same. You have AN at the end. Right, so this is this action. So that's just a review of what the notation meant. I think we get back to permutation groups later. They become more useful later. But before we deal with specific kinds of groups, it's good to go over just some basic properties of groups. So we're going to go over a few basic properties. I'm going to give you some time to think about why they might be the case. And then after a certain amount of time, I'll give you a proof. Hopefully you can come up with a proof yourself. Again, just as notation, if I write G1, if we have a group G and elements G1, G2, then writing G1, G2 is not the same as writing G2, G1, right? We don't necessarily have commutativity. And the way we're going to read this is if I write one of these, say this one, what this will be interpreted as is the action do G2 first, and then do G1 to the resulting element. Okay, so it's going to be like a function composition. The thing on the inside gets done first with the way that we write functions. So I'm going to keep this standard up. You could get away with doing it the other way, but it gets messy with the way some books write it, and I think the way the convention is naturally, this is how the composition typically is written. So we're going to keep up this standard. So when I write, just say G1, G2 of X, it means G2 of X and then G1 of that. Yeah, it's just a notation piece. Now we can actually get into the properties of groups. Let's say you have a group G. Remind me, what are the properties that this group has to satisfy? If it's just an arbitrary group, we don't know anything else about it.
Wait, commutativity is not a property of a group? Because
yeah, commutativity is not. Commutativity is a property of abelian groups or commutative groups, right? It's a property that you can add on, but it doesn't, it's not essential to a group structure. I should say a group with an operation. So what are the necessary conditions to have a group with an operation?
Associativity.
Yeah, so you have to have associativity.
Identity.
Yeah, associative, meaning that A dot B dot C, the dot is just the operation, right? Means this is the same as this. Okay, you said identity.
Yep.
And what's the property for the identity? Like, what does that mean?
It's like basically like the operation you do to get the same thing. So for like multiplication, multiplying by 1, or divided by 1, or doing mod, like, I don't know, mod 0.
Yeah. So you have seen this notation, right? For all, and there exists.
Yeah.
Yeah, so there exists an element. Usually we use E for the identity element. Sometimes people write just id. But there exists an element in G such that GE equals G equals EG for all G in big G. Right, so it's just the element that does nothing, right? It's the element that is the identity. So group elements commute with the identity, right? Just because it's the identity. They just don't commute generally. So yeah, we have identity.
Inverse.
Inverses. And what does this mean?
It's not like reciprocal. It's like, how do I say it? Oh, wait. Is it the one that you multiply by something to get the identity?
Yeah, it's saying that for all elements in the group, for all G and big G, there exists G prime, some other element in the group, such that G prime equals G prime G equals E, the identity.
And closure. Closure.
Yeah. So that's inverses, and that's essentially it. The fourth one that is kind of assumed was closure, which is that if X, Y are in G, then the composition of the two is also in G.
For inverses, what do you say instead of multiplication? Like, is it an element of the group that when you do a certain operation to it gives you the identity?
Yeah, whatever the group operation is.
Okay.
So depending on the group, the operation will be one thing or another thing, but it's just whatever the group actions are. So a lot of the time it's composition. Composition is it's an intuitive one for us to use. For arithmetic, it's addition, multiplication. For some geometric shapes, for example, you could get rotation, reflection, things like that. Like we had earlier when we were studying the equilateral triangle, right? What was the inverse of the reflection action across a line?
The inverse?
Yeah, what was the inverse of the reflection?
I don't remember.
Well, it was just itself, right? Because if you do a reflection twice, you get back to where you started.
Oh, okay.
So in that case, the reflection is its own inverse, right? If you do it once, then what's the element that you have to do to get back to the identity? Well, in this case, you do the reflection again. For rotations, it was other things. But the idea is it's whatever this dot is, right? Whatever the operation
Oh,
is.
okay. It's whatever you do to get back to what you started at. So,
Yeah.
okay, that makes sense.
Yeah. Regardless of what the operation is. That's how inverses are defined.
All right.
Okay, so these are the 4 properties. So now, with these 4 properties, there's enough to prove some basic properties, extensional properties of these groups, apart from just these basic 4 axioms. So let's go over the first one. The claim is that there's a unique identity for every group. For every group G. This is the first claim. Every group has its own unique identity. Now, how do you prove the uniqueness of an identity?
Wait. Well, if they have this, oh wait, if they have the same identity, they're just the same group, right? Like,
not necessarily. That's a little different from what this claim is stating. So, like the reals under multiplication and the integers under multiplication, they both have the same identity, right? 1. But they're different groups.
wait, then they're not a unique identity, are they?
No, but for given the group, instead of not given the identity, given the group has only one identity element. So if I give you the reals under multiplication, what's the identity? It's the element 1. If I give you another group under a different operation, you know that there is an identity, right? Just because it's an axiom, it's a group, so it has to have an identity. But how do you know that there's only one identity, right? Why can't you have 2 identities or 3 identities that are different from each other?
How do I prove that?
Yeah, so this falls under a broad class of problems where you try to prove uniqueness of something, right? That there's only one of something. Typically, the way we do this is you say, suppose there's multiple, right? Say that there's 2 identities, E1 and E2.
Oh, contradiction.
And then you try to prove that they're the same, right? And then the conclusion would be you can't have 2 that are different. If you have any set of identities, they're all the same identity. Therefore, there's only 1. So that's how we're going to go about trying to prove this. You suppose that there's 2. I mean, you could do it with 3 or 4, but I mean, if you do it with 2, that's sufficient because you could just do pairwise on all the rest of them. So suppose there's 2 different identities. Then you want to prove, right? Your end line is going to be that they're the same element, right? E1 equals E2. So for sets, this kind of makes sense, right? If you have a group that you're doing actions to, it makes sense that there's only one do nothing action, right? It makes sense that there's only one element that doesn't change anything, right? Because if you have 2 things that both don't change anything, it makes sense that they'll be the same, right? They're both just do nothing. But how do we prove this? So go ahead. Sorry. Go
Can
ahead.
you assume that they're different? Can you be like,
you could assume that they're different. That's how the proof. Like if you assume that they're different and then prove this line at the end, you'll have a contradiction,
yeah,
which you would then conclude that they're the same. But even if you don't assume that they're different, Like, let's not assume that, and you go through the same proof. What's the concluding line?
Well, you want it to be they're the same, right?
Right. The concluding line is this thing at the bottom, right? So you don't have to assume that they're different. Because if they're the same, then the result will just pop out that they're the same. So you don't actually have to make the extra assumption that they start out different. Because the proof is going to be the same, even if they are the same.
So would it be something like some element, I don't know, like operated with E1 will give you just the same element?
Okay,
right?
yeah, so let's give a name to this element. What do you want to call it?
Just like A.
Okay, so we'll consider A. We'll consider AE1.
Yeah.
Okay, well, this is A.
And the same thing would be A2 equals A.
Yeah, AE2 equals A. Okay, so what can we do with this?
Well, we don't have commutativity, right?
Right, you don't have commutativity. In fact, we'll almost never have commutativity, except under some very special cases.
Yeah, I don't know.
All right, well, let's see what we can do from these two lines. So you can combine these, right? You can set them equal to each other because they're equal.
Oh yeah.
So you'll have AE1 equals AE2.
Yep.
Okay, so this is close, right? It's not exactly what we need, but it's close, right? We're trying to get E1 equals E2. Now, what if I multiply both sides on the left-hand side, by A inverse, right? Because A has an inverse. It's a group property.
Oh, yeah, yeah.
So multiply it by A inverse here. And notice it actually matters what side you're doing it on, right? It matters if you do this on the left or on the right.
Yeah, because it's not commutative, right?
Right, because you don't have commutativity. So as long as you keep left and right multiplication, as long as you keep that in mind, you're allowed to do it. In this case, we're doing it on the left. Then we have associativity now as well, right? So I can group them like this. Yeah.
Yep.
And what is A inverse A?
One. Wait.
Yeah, one for arithmetic, but in groups it's
So wait, what? A? It's not A.
it's not A. What's an element times its inverse?
What? Isn't it one? Am I missing something?
Well, not one, because we're not working with arithmetic, right? We're not working with the real numbers of the integers, right? This is an arbitrary group.
Oh, the identity.
Yeah, it's the identity, right? So like one,
crap.
but for a group. So A inverse A is the identity, but we don't know if it's E1 or E2 yet, right? We just know that it's an identity. So I'm just going to write id for now. This is id E1, E1 equals id E2. Or I guess I'll write id1 and id2 because they could be different. But let's look at this. What is the identity times E1?
The identity times itself? Or
Well, we don't know that they're,
yeah, they could be different.
yeah, they could be different. But what do we know about this? It's an identity, right?
Yeah.
Therefore, it keeps this the same.
Uh-huh.
So this left-hand side is E1.
Oh, okay, yeah. Okay.
Now, we don't know if this identity is a third, maybe it's a third identity or a fourth identity, but it's an identity. Therefore, it fixes E1. Similarly, on the right-hand side, id2, which could be E1, it could be E2, it could be a third, fourth, fifth identity. It's an identity. Therefore, it fixes E2. So what is the right-hand side?
E2.
It's E2. But this is what we wanted, right?
Mm-hmm.
So this actually this is the proof that they're unique. So in this case, we get that E1 and E2 are actually the same. So you don't have to worry about having multiple different identities in a group. There's only ever one. Do you understand how the uniqueness argument works?
Yeah. That there's only one identity for.
Yeah, you're supposing that you have just two separate things, and then if you prove that they're the same, which is what this argument does, if you prove that they're the same, then those two separate things are actually, one and the same thing.
Yeah, for some reason I thought it was like distinct. I don't know why.
Yeah, you don't have to assume that they're distinct. You can. If you assume that they're distinct, it'll just turn into a proof by contradiction. Like if we assumed this at the beginning, then we just have a contradiction, right? And then what would the contradiction prove? It would prove that this thing was false, right?
Wait, what? I thought you were trying to prove that that's correct.
This thing, not equal.
Oh, yeah.
Like if you assume not equal and then you get a contradiction, what does that prove? That they are equal.
Yeah.
But that's what we're doing anyway.
Mm-hmm.
Okay, so that's uniqueness for the identity. So we have that there's only one identity in any group. There's actually a slightly shorter proof. You still start with E1 and E2. So you have E1 and E2 are identities, but then you just consider the product E1, E2. Now, E1 is an identity, right?
Mm-hmm.
So it fixes E2.
Yep.
Therefore, this is E2 on the right-hand side.
Yep.
But likewise, E2 is an identity. Therefore, it fixes E1. So this is also E1. But then these two are.
I thought we don't have commutativity. So I thought we don't have commutativity though.
We don't have commutativity. But remember what the identity does, right? If you have an identity E times a group element G, this is G, which equals GE. Right, these are all the same.
Oh, so the order doesn't matter for the identity?
Yeah, because it's the do nothing element, it's the only element that has to commute with everything.
Oh, okay, all right.
So identities commute through.
Okay.
And in particular groups, maybe you'll get other elements that commute as well. I think there's a specific name for those kinds of groups, but in any group, identities will commute. That's it's a corollary of this. But this is uniqueness. So you don't have to worry about multiple identities. Another nice thing is that you don't have to worry about multiple inverses. So if we had a group element G in a group big G, we knew that there was a G prime such that G prime equals the identity, right? Like this, yeah?
Yep.
Now let's suppose that there's another element, G double prime, that does the same thing, right? G double prime is an inverse of G. Right, so we're supposing here that G has two different inverses, right? One of them G prime, one of them is G double prime. The actual statement is that inverses are unique.
But the inverse commutes as well.
Hmm?
The inverse also commutes.
Inverses don't necessarily commute, no.
But in this case, they do.
No, we're just going to get that they're unique. So we're just going to get that there's not more than one inverse for any particular element. So if I give you a set like the integers and I ask you what's the inverse of the element 3, right, there's -3. And this part of the theorem says, and nothing else. There's -3 and nothing else, right? Just -3. Now for the integers, that's kind of obvious, right? But in other groups, it's not so obvious. How would you know that there's not multiple inverses for the same element? So if I gave you the, what was a group that I gave you? Like the equilateral triangle. Rotation clockwise by 120 degrees, like 1/3 of a full turn. If this was my action, what's the inverse action?
The opposite way.
Yeah, rotation counterclockwise by 120 degrees. And this theorem says nothing else is the inverse. That's the only inverse.
Okay. But I don't get why you like put G prime equals E equals G prime G when you said it doesn't have to commute, or it won't. Is that just an assumption?
Oh, it commutes with G. It commutes with its own inverse, just because their product is the identity.
Gotcha. Right.
So it doesn't commute in general. It just commutes with its own inverse because their product is just the identity no matter how you put them together. Right? They're inverses of each other. So when you have two things that are inverses of each other, you could do one part and then its inverse, or you can do the other part and then its inverse, right? Both of them just take you back to the identity. So again, it doesn't commute generally. It commutes in a very specific case. So how are we going to prove that inverses here are unique? What are we trying to prove here?
There's only one inverse.
Well, yeah, but like what's the mathematical conclusion? Like in the last case, it was that we were trying to prove that E1 equals E2, right? That the two identities were the same.
G double prime equals G prime.
Yeah, the last line here is going to be G double prime equals G prime. Right, same structure. Because almost all uniqueness proofs have the exact same structure. Almost all of them. So how might we do this?
You could do like basically the same way we did last time. So like G prime equals an identity. So like E1.
Well, now we know that it's the only identity, right? Because from the last
Oh.
part, we proved that there's only one. So now we can just write U, right? We don't have to worry about multiple.
Okay.
Okay, so it's equal to E, yeah.
And then same thing with G double prime. So G double prime equals E.
So G double prime is also E, yeah. And then from here, what do you do?
You can set them equal.
Yeah, and notice that this step of setting them equal, you actually need that there's only one identity, right? If you could have two different identities, then they wouldn't necessarily be equal, right? You could have G prime be one of the identities and G double prime be the other identity.
Yeah, that makes sense actually.
So now that we know that there's only one, we can actually do this setting them equal to each other step, and we get that G prime equals G double prime. Okay, cool. And what now?
You multiply the identity.
You can try that. You can try multiplying by the identity on both sides.
I don't think that would do anything.
If this gets you somewhere.
No, I don't think it does.
You can multiply by something else on the left.
Can you do the inverse again?
Yeah, you can multiply by an inverse, and it actually doesn't matter which inverse. I'll just pick G prime.
Yeah.
Then by associativity, I can group them like this. And what are both of the things in the parentheses?
The identity.
Right, so this becomes E G prime. This becomes E G double prime. But then this is just this step, right?
Oh, yeah.
Because they're identities, so they fix both of the elements.
So the step where you multiplied again by an inverse, those inverses could be different, and it doesn't matter because they both just give an identity, right? Or the identity.
Yeah, they give the unique identity. And then you get the convenient canceling. So this proof of uniqueness, what it allows us to write validly is now instead of writing this G prime that I've been doing, we can now just write G inverse, right? We write inverses like this, right? No, for arithmetic, this means 1 over something, blah, blah, blah. But in general group theory, it's just whatever the inverse is. And now we know that this is actually just a unique element, right? It's not multiple elements, right? It's one thing now, just whatever the inverse is. Does that make sense?
Yeah.
Okay, so that gives us uniqueness for inverses. We have, it's our third general property. Let's say I have elements A, B in G. And let's say I want to consider, so A B is a product, and then I want to consider the inverse of this, right? The inverse of the whole thing. I could just tell you what it is, but I don't think I will. Can you figure out what this is? You can write it more simply anyway. Like a lot of the time when people ask questions like, what is something, right? The trivial answer is just to like repeat back what they said to you, right? You just say that's what it is. But typically when people say it, they mean, can you reduce it to a simpler form, right? So can you reduce this to a simpler form? Or do you have any guesses?
This is multiplication, or is this just like an arbitrary operation?
Our arbitrary operation. A lot of the time they just use the dot for arbitrary operation and multiplication. It's kind of an overused symbol just because it's so simple.
Oh.
But here I'm using it as an arbitrary operation.
Well, couldn't you just make that into like the unique inverse that the group has?
Say it again.
Couldn't you just make that into the unique inverse that the group has?
Right, it has a unique inverse. But like if I asked you to write out what that inverse was in terms of A and B.
Yeah, I don't know.
Okay, so if we were working with regular multiplication, this would be A inverse times B inverse, right?
Yeah.
Inverses go across, they travel across multiplication. It doesn't work like this for groups. It almost works like this for groups. So we'll see what it is exactly. What do we know about A times B all inverse? Well, we know that if we multiply it, I say multiply, but I just mean do the operation. If we do the operation AB, what should we get?
The identity.
Right, the identity. Okay, well, I can drop these parentheses around AB, right? They're not, there's no inverse outside of them. I'm not losing any information by dropping them here. So here, I want to multiply on the right. I'll move this over so I have space. I want to multiply on the right by B inverse. Yeah. Valid.
Yep.
So this left hand or the right hand side is just B inverse, right? And what does the right hand side become? What does the left hand side become?
A times B parentheses inverse, and then just A.
Yeah, A times B all inverse, and then this part goes away, right? Because they cancel, and then times A. Well, I can do something here. I can multiply on the right by A inverse now. Yeah?
Mm-hmm.
What's the left-hand side?
Just A parentheses A B parentheses Inverse.
Yeah, so we get back what we were trying to identify, and the left-hand side now is this, right? And this is the reduced form.
And those
Notice
two
it's similar, right, to what we had earlier, right, to the way it works for regular multiplication.
Mhm.
And now you could tell me why it works for regular multiplication, right? Now that we have this, multiplication we know is commutative. So we can switch these. Right, on this right-hand side, we can switch these two. And we'd get what we're familiar with. But for groups in general, you can't switch them, right? Because you don't have commutativity. So if I have an element G1, G2, a product inverse, well, then this product is G2 inverse times G1 inverse. So the inverse passes through the parentheses, but you have to switch the order, is the shorthand way of remembering.
Mhm.
So does this proof make sense?
Yeah.
Yeah, so a lot of these are just messing with the, I mean, it looks like algebra, right? It is algebra. It's right, right. It's why it's called abstract algebra, modern algebra. Abstract algebra, modern algebra might be something else. I think it's actually modern algebra might be group theory as well, but it looks like algebra because it is algebra, right? This is abstract algebra. Okay, so if this one makes sense, then go to the next one. Clear. There we go. This one should also be pretty intuitive, but if I have A, or I'll use G actually because we're talking about groups. G inverse, and then the inverse of that, what do you think this is?
G.
Yeah, it is G. You do have to prove it, but it shouldn't be that hard to prove. And it's fairly intuitive, right? The inverse of something's inverse is itself. That's what inverses do. But the proof, how would we prove this? Well, let's see. We'll take G inverse and multiply by G inverse inverse. So what will this be?
G inverse.
It's not G inverse. Notice I could replace these G inverses with, say, like a dummy variable like K. And what would it read as?
K times K inverse.
Which is?
The identity.
Yeah. But we also know that the identity is G inverse times G, right?
Mm-hmm.
So now we know that like we can cut out this E in the middle. So now we know that these two are the same. And now I multiply on the left-hand side by G. And now you can see the cancellation, right? This cancels, this cancels.
Yep.
And what am I left with?
G inverse equals G.
Right, and then you're left with this. So the inverse of an inverse is, as we expect, the thing, right, whatever the group element is. So this one's fairly straightforward. Does this make sense?
Yeah.
Okay. Is this part worth going over? Okay, so this one's we've kind of been using this one, but it's convenient to just use to write out. If I have AB equals AC, what can you tell me about like what can you tell me from this? What's the intuitive thing to do from this?
Divide by A.
Right, divide by A.
Multiply by inverse on the left side.
Right, multiply by A and inverse where though? It actually does matter.
Left side.
Right on the left side, so we multiply by A inverse, A, B, A inverse, A, C. This becomes B and this becomes C. This is called left cancellation. If you ever see anything of this form, we typically go straight to this. Right, we don't show this step in the middle. For this reason, right? Just this whole property, doing it in general right now, it allows us to cancel things that are the same on one side. Does that make sense?
Yeah.
Notice, of course, you can't do this if it's like this. Right?
Yeah, so we commute.
Yeah, no commutativity. You also get right cancellation for the exact same reason. If you have BA equals CA, you do the same thing. You multiply, in this case, on the right by A inverse. And then what do you get? You get B equals C as well. So these cancellation properties, they're kind of tedious to write out over and over. So doing them here, we're just assuming them now for the rest of group theory, right? We have left and right cancellation, which is convenient. It's not like mind-blowing, it's not surprising in any way, but it is convenient to use. Does that make sense?
Yeah. Makes sense.
Right. This is some notation. If I have an element G in G, and I have a natural number N, we're going to define G to the N. We're going to define exponents here. And what is an exponent? It's going to be G times G times dot, 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 G. And how many of them are there? There's N of them. So similar to how we define exponentiation typically, right? Except this is not hard multiplication now, right? It's whatever the group operation is. And here we actually do need N to be a natural number, right? It doesn't make sense for it to be it doesn't make sense for it to not be an integer here. In analysis and in number theory, you can come up with ways to define exponentiation without the exponent being an integer. When we're doing group theory here, all we're using exponentiation for is shorthand for repeating the operation. We're not using it in any other way than as shorthand for this. Does that make sense?
Yeah.
And what we actually get from this is that a lot of standard exponent rules actually still hold. So like g to the m plus n. Well, what is this? It's g, right? All these g's. How many of them are there total? Well, m plus n, right? How many are here? M. How many are here? N. So what does this become? It becomes g to the m times g to the n. So this is a standard form, right? This is a standard exponentiation rule, and it actually holds here, even with this different notation. Does that make sense?
Yeah.
Similarly, if you have g to the m all to the n, what is this typically? It's g to the mn, right?
Hmm.
And you could prove it the same way, right? If you replace g to the m here with multiple g's, and then all to the power n, well, how many g's are you getting at the end? You're getting nm of them, right?
Yeah.
So because we have some of the basic structure of arithmetic to incorporate here, because it's been set up by past mathematicians, we get this convenient notation for writing repeated operation. So this is useful. Those are most of the properties. Here's an example of a property that doesn't hold. For standard arithmetic, we have that, actually I shouldn't use g because I have multiple things now. If n is a natural number, ab to the n in standard arithmetic is a to the n times b to the n, right? This is not true necessarily for groups. What is ab to the n? It's ab, 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 ending with ab, and then there's how many like individual terms are there? There's two n terms here, right?
With two n.
Right, NAs and NBs.
Oh, if you're counting A and B separately, yeah.
And notice that they don't recombine like this. This doesn't happen because we don't have commutativity. Does that make sense?
Yeah. Wait, they don't combine? So there's more if you do AB parentheses N than if you do AN BN?
Well, they don't combine like this, I'm saying. Because what is this in terms of group theory? It's A.
Oh
Some number
yeah,
of
because it's
times,
nothing. Yeah, because nothing.
followed by some B's. Right?
Yeah.
These
Okay.
are not the same.
I know what you mean by they don't combine. Yeah.
Yeah. So this is an example of an exponent law that doesn't hold. But as long as you're careful with what does hold and what doesn't hold, it's typically convenient. So like some basic manipulations that you could do with this. I could write this as A, B, dot, 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 B, and I'm grouping them like this. And I could write this as A, B, A to the n minus 1, B. Do you see why this is valid?
Yeah.
It's just associativity and recombination, keeping the order the same, right? You don't get to necessarily switch order here. So these two actually are the same, even though they look, different. This one that I just did, it's not useful. It's not a useful thing, but it's a true thing. If you ever needed it in a proof, it would be there. Unlike this one doesn't hold. Does that make sense?
Yeah.
Cool. There's one last notational piece, and then we'll be done. We can write this as what this means if I write here n is a natural number. What this means is G inverse times G inverse times G inverse. And then how many G inverses are there? There's n of them. Does it make sense?
Yeah.
And just to clarify, like if we multiply G n times G to the negative n, what should this be?
Well, it would just be like a bunch of G's and a bunch of G inverses because they don't combine, do they? Or
Do they? I'll just draw 4 because I don't, like, you'll get the point.
oh wait, they do combine because the identity commutes, right?
Yeah.
I mean, the inverse.
In this case, they do combine because the middle collapses, right? So these middle two collapse, these outside two collapse, these collapse, and the outside ones collapse, right? So at the end, you just get the identity. But if we have our addition laws, this is G to the n minus n, which is G to the 0. So this is how we would write 0th powers. Even though 0 is not a natural number, we just define G to the 0 to be the identity. So, similar to regular multiplication in that way, right? If you have an integer to the 0, what is it? It's 1. Which is the identity. But you get it more generally here in groups as well. Yeah, I think that's it for today. We went over decent number of group properties. So we'll make use of those later. We're going to talk about other things that you can do with groups.
All right. Yeah, I kind of had some brain farts today. I didn't remember what we did last time. It was like 3 weeks ago.
Yeah. Well, I slept in and then I didn't get around to scheduling something else, but we'll just be back on for Thursdays like normal.
All right.
All right. Yeah, that's it.
All right, see you.
See ya.